Hi, everyone. It is my great pleasure to introduce our first invited speaker, Ronitt Rubinfeld. Ronitt is a professor at MIT and Tel Aviv University, computer science department, and I'm not sure how exactly she does that. For all I know, she might be using some secret quantum superposition technology. Ronitt has graduated from UC Berkeley. She's a famous student of Manuel Blum, who is famous for having many famous students. Ronitt has made many significant contributions to theoretical computer science, but she's probably most well known as the founder and CEO of property testing business. She has started it with Manuel Blum and Mike Luby in 1990. Their first product could only test linearity of functions, but it soon had some very important customers, including the whole area of probabilistically checkable proofs and hardness of approximation. Since then, her business hired many more people. They expanded into other properties of functions, properties of distributions, and properties of graphs. She's also a leader in the area of randomized algorithms and sublinear algorithms. She's not new to learning theory. She actually made many significant contributions, especially in its early days. She published in Colt about 20 years ago, but she has been mostly absent since. So since she has been absent, I hope she will now tell us what she has been up to during those years. Please welcome her back.
Okay, does this work? Oh, there, okay. Do you hear me? Okay, good. Well, thank you. That was pretty much the nicest introduction I've ever received. And it's good to be back here. So what I'm going to talk about today is testing properties of really big distributions. And when I say really big, I mean that the domain is a very large size, okay? So let me just, so that we have an example running in our heads, let's talk about the lottery, okay? So if you want to play the lottery, you'd want to know that it's fair. So what would you mean by fair? Well, you'd want to know that the draws are independent. You'd want to know that it's uniform. And here's actually a case where a lottery went awry, okay? So there was this Polish lottery, Multilotek, which is basically this big machine. It's a physical machine, and it's got these balls in it, 80 balls, numbered 1 through 80. And every day that they run this lottery, they take out 20 balls. And that's, when people bet on these things, okay? Well, the initial machine was biased. The probability of 50 to 59 was too small. And since every day they're taking out 20 out of the 80 balls, a quarter of the balls, you get to see this pretty quickly, and people realized this and made a lot of money on this lottery, okay? So they fixed it. But they could see this quite quickly that there is a problem. All right, well, what about the New Jersey Pick 3 or Pick 4 lottery, okay? Well, what's the Pick 3 lottery? You pick 3 digits in order. Okay, so you have 1,000 options. For Pick 4, you have 10,000 options. And let's just give it to them. Let's assume that they picked their lottery draws IID, and that all we're worried about right now is figuring out, was it uniform distribution? Okay, so we did this experiment in 2000. At that point, Pick 3 had been running since 1975. There were 8,522 trials. Actually, Joe Killian did this. He went in the past draws of the Pick 3 lottery. He ran the chi-square test from Excel at the time. So this would be, I guess, Windows 2000. And got 42% confidence. Why? Because we only had 8.5 times the domain size many draws of the samples, okay? So that only gave 42% confidence. 4 was even worse because it started running later. So we actually had 6,544 draws since it started, but the size of the domain is 10,000. So on that, Microsoft Excel said no confidence, okay? So now the question is, can you do better than this? So here's the general paradigm. You're given a distribution on a very large domain, and what you need to know various things about this distribution. You want to know Is it uniform? What's the entropy? How many distinct elements in the support size? What's the shape? Is it monotone? Is it bimodal? Is it k-modal? Is it close to uniform? Is it Gaussian? Is it Zipfian? Is it generated by a small describable generator? Is it one of any other type of class of distributions? Okay, how can we tell these things about the distribution? We don't want to make a priori assumptions about the shape of the distribution. Like, we don't want to assume that it's smooth, monotone, normal, whatever. And these are fundamental questions that have been considered in statistics, information theory, physics, machine learning, as well as pretty much anywhere else. People care about these types of questions. Okay, so our question today is, how many samples do you need for these problems in terms of the domain size? And in particular, the question we're interested in is, do you need to actually learn the distribution explicitly? Do you need to take enough samples that you can estimate the probabilities of each domain item? Or can you come up with an algorithm that has complexity that's sublinear in the domain? Okay, so that's our aim. Sublinear sample complexity. Okay? All right, so here's the model. We're given this distribution. Let's call it P. Sometimes we'll call it Q, but normally P. It's given to us as a black box. Okay, it's blue there, but it's a box. Okay, you press a button, you get a sample. Okay, okay, you get a sample. It's IID. Each time you press a button, you get a new IID sample. Okay, and let's assume that the domain. I just want to talk about the size of the domain. So let's assume for right now that the domain is 1 through n. So we're just going to arbitrarily label the elements of the domain as 1 through n. And we'll use P sub I to be the probability that P outputs I. But of course, we don't know these P sub I's. We just get samples. The box better know this P sub I's, but we don't, okay? All right, and now there's some kind of test. We're trying to figure out something about P, and we're interested in the sample complexity in terms of n, okay? Well, there will also be some epsilons and deltas later too. We can talk about that. But for right now, what we care about is complexity in terms of n. Okay, so let's begin with a first set of basic properties, which has these properties, we're going to call them similarity of distributions type properties. Okay, so let's just start with you're given a distribution P. You want to know, is it close or far from some other distribution Q? Okay, and now this question is going to vary depending on what we assume about Q. For example, Q might be known to the tester. It might be like the uniform distribution, or some other distribution where the tester knows the value of Q sub I for every single value of I. It doesn't need to query Q sub I. It doesn't need to take samples. It just really knows Q completely. Okay? Or we could assume that Q is also given via samples. You have 2 black boxes now, one for P, one for Q, and you have to figure out, are they close or far? So that's 2 options. We're going to talk about both. So let's start with the uniform situation. It turns out that actually this uniformity test is something that we can do in theta of root n time. Okay? So, but what does it mean that we can do? It means that we can distinguish the case where P is uniform distribution from the case where P is at least epsilon far in L1 distance from the uniform distribution. Okay? So it either has the property of being uniform or is epsilon far from being uniform. And this is something we can do with square root n samples. Okay? And just to give an idea of how this was first found, I just want to mention an idea of Goldreich and Ron, which they were interested in estimating the L2 distance square from uniformity. And they wrote out the L2 distance squared of P from a distribution. It's just that thing. So if you work this out, the L2 distance square of P from the uniform distribution, you just do some little algebra calculations and you get, and this is very simple calculations, I didn't hide anything here, but you just get that the L2 distance square is equal to the collision probability of the distribution minus 1 over n. Now we assume we know this. Okay, so we know this. So in order to estimate this, I just need to estimate the collision probability. Okay, so very nice. So what we're going to do is estimate the collision probability to estimate the L2 distance from uniform. Okay, and then what we'll do later is use the fact that L2 distance and L1 distance have a relationship to get a bound on the L1 distance as well. Okay, so that's how we're going to do it. And you might ask, well, how can we estimate the collision probability? This was just another nice idea of Goldreich and Ron. To estimate the collision probability to within 1 over n, you actually can do this with square root n samples, because when you get square root n samples, you actually have square root n choose 2 pairs of samples. So that's how many estimates you get of the collision probability. And okay, they're not independent, but they show that the variance is good. So, they bound the variance, and it turns out that that gives you an extremely good estimator. Okay, so that's why square root n is good enough, pretty much. I mean, it's not the whole story, but it's a start. So that implicitly gives you a root n over epsilon to the 4th upper bound via collision probabilities. It's fairly easy to see that there's a root n lower bound on this problem as well. Why? If you take the uniform distribution on n elements and compare that to the uniform distribution on a random subset of n over 2 elements. Okay? Well, it takes you a while to figure out which one you're getting samples from. Okay? So in one case, you could be getting samples from the uniform distribution, or you could be getting samples from a uniform distribution on a random subset of n over 2 elements. How are you going to tell the difference? You're going to get these samples, and because it was a random subset, you can't tell anything from the labels of the elements that you're seeing. So all you can really see is when you get your first collision. And these two distributions are really far from each other. One is uniform on the whole domain, and the other is uniform on only half the domain. So their L1 distance is 1. That's quite far. On the other hand, you're only going to start seeing collisions at root n samples. That's the first time you start seeing a collision. And that's the only thing that's going to allow you to distinguish when that between the two cases, is when you see that first collision. Okay? And so you can make this formal, what I just said, and that gives you a root n lower bound. Okay. It turns out Paninsky, who is from Columbia, actually, Columbia Statistics Department, University of Columbia, not Columbia, the country, he actually gave an upper bound of root n over epsilon squared, assuming a lower bound on epsilon. But his tester was a little bit different. It still uses a type of collision statistics. Instead of looking and counting how many collisions we have and estimating the collision probability, he counts the number of distinct elements, which, as you can imagine, it's related, right? Okay, so I'm still going to call this a collision statistic, even though it's not the number of collisions, okay? And by counting the number of distinct elements, he gets a better bound in terms of epsilon, and also using other techniques shows a lower bound of root n over epsilon squared. Okay, and actually very recently there's been some more work showing that chi-square test in Microsoft Excel might actually be a little bit better than we thought. So not quite the chi-square test, but similar to a chi-square based test was shown to actually give optimal results. So these sets of works give optimal results based on a test that's similar to the chi-squared tester. So don't throw out your Excel. Well, maybe throw out Excel, pick these guys instead, but it's not so different. And actually, very recent unpublished work by these guys has shown that also the collision-based tester, the one that just counts the expected collision probability, the one that, like really counts the probability that you get two of the same, I know I called this a collision statistic, but I really mean the collision-based tester in the first bullet, that one actually gives you optimal results as well. Okay, so back to the lottery, we actually do have plenty of samples, okay? So let's take this and generalize it a bit more, okay? So we just saw that testing whether a distribution is uniform takes theta of root n samples. It turns out that you get nearly the same complexity to test if P is any known distribution. So like if you give me a table and tell me P of 1 is supposed to be this, P of 2 is supposed to be this, and so on, you can test also in theta of root n for any known distribution. Okay, I'm just going to say that the first tests were based on collisions by reducing to the uniformity case. In other words, by looking at Q, remember Q is known to you in advance. You don't have to sample to learn Q. So you could put together similar probability elements, and then you can create logarithmically many buckets with similar probability elements, and then you can do log n uniformity tests. So that was kind of a reduction to log n uniformity tests, but that was improved quite a bit using chi-square testers, and even using collision testers, but without bucketing. And right now, there's a new work showing a much simpler bucket avoiding reduction, which is, so there's some really, so basically there's been, all of this work has happened just in the last few years, last couple of years. So there's been a lot of exciting work in this direction, making it simpler, making it better, and also showing that different kinds of testers do really well. Okay, before I leave this notion of testing distance, I want to mention something about what happens when both P and Q are given via samples only. So you don't have Q written down now. You don't know anything about it. You're just getting a sample of P or a sample of Q, whatever you want. Okay, so you have two boxes, and here we thought, oh, this is also going to be root n, and we couldn't get it, and we kept like, well, maybe we made a mistake in the calculation. So there was like a whole month of just checking and checking and checking, and sometimes we got root n, and that turned out to be the bug. But we checked and checked and checked, and we couldn't figure out how come we're not getting root n. What are we doing wrong? What are we doing wrong? What are we missing? There must be something simple. Well, it turns out that it's not so. There's a reason why we weren't getting it right, and that's because it is theta of n to the 2/3. Okay, so when you don't have Q explicitly, then actually the right sample complexity is theta of n to the 2/3. Okay, why is it so different? Well, you can show that in all these testing problems of symmetric properties, the collision statistics are all that matter. Either the number of and when I say collision statistics here, I mean the number of elements that appeared exactly once, the number of elements that appeared once from Q 0 times in P, the number of elements that appear 2 times in Q, 3 times in P. That's what I mean by collision statistics. For all ij, the number of elements that appeared I times from P and j times from Q. Okay? So that's what I mean by collision statistics. You can show that that's all that matters for symmetric properties. Okay? And you can construct families of pairs of distributions which have heavy elements, and which the pairs are always going to be identical. And these heavy elements are something like 1 over n to the 2/3 probability. And they're going to have lots of light elements, which have something like some constant over n probability. And they're either going to be identical. The pairs are either going to be identical on the light elements or very different, like 0, no intersection on the light elements. Okay, but all you can see, you don't. Then you randomly relabel the names of the elements. So now what can a tester do? A tester can look at the elements and it sees, I got 10 5 times. But usually that won't happen with the probabilities I just gave you. But I got 10 once, I got 11 once, I got 22 0 times, from P and twice from Q. You can see statistics like that, but the names don't tell you anything. The only thing that tells you anything is the collision statistics, because the names were randomly relabeled. Okay, well, now what happens with the collision statistics? It turns out that whatever happens with the heavy elements completely swamps what happens with the light elements. But the heavy elements were the same in the pair. Okay, so you can't really tell whether the light elements are distinct from each other or identical, because it's completely swamped out by the heavy elements. All right, so that's essentially how you show this lower bound. I'll just say something. That's essentially that's how you construct the families. Showing that they actually prove a lower bound was quite a bit more difficult. And in fact, our first attempt and our second attempt and our third attempt were not so what was claimed in the proceedings versions is not right. And Paul Valiant finally fixed the situation for the lower bound and gave a real omega n to the 2/3 lower bound for constant error. And so that nearly matches the upper bound. Then in more recent work, this is in the last couple of years, maybe not couple anymore, I guess I'm getting old. 3 years. Okay, so 3 years ago, tight upper and lower bounds were given for these problems. Again, n to the 2/3 with this epsilon to the minus 4/3 dependency. And I should say that the lower bound has been simplified dramatically since this one, which is good news, believe me. And the upper bound is also, there's a much nicer way of viewing the upper bounds, also very new published work by Diaconopoulos and Kane. Okay. All right, so we've talked about the property testing problem in 3 different settings. But what if you say, okay, listen, I want to use this property testing problem to see if I want to estimate sales and I want to figure out, do I need a new ad campaign? And I know that June, July sales are roughly the same, but I want to know, are they different enough that I need to come up with a new advertising campaign? Okay, so what I don't want to test, I don't want to distinguish 0 error from epsilon error because I know there's error. I want to distinguish epsilon error from 2 epsilon error or epsilon error from 1 minus epsilon error. Can I do that? Well, that's much tougher, okay? So that needs theta n over log n samples, okay? So estimating the distance is n over log n, and that's tight. There's both an upper and a lower bound, and this is really nice work. This should be squared because there's 3 papers. There's a lot of papers, and they're in 2011. So again, these algorithms are based on looking at the collision statistics and writing an LP to see if you're getting some kind of right or wrong behavior. The lower bounds are also based on looking at this collision statistics and finding new analytical tools because things are not independent. This was at the time a very long proof. This new analytical tools thing, it was about a 40-page paper. I should say that I'll say it later, but the techniques here have been simplified by Wu and Yang, who are more from the information theory crowd. And there's much easier tools for showing such lower bounds at this point. Okay, and this is recent as of last summer. Okay, so we'll get to that again. I want to mention independence. Here we're given a joint distribution. Let's just say on pairs for now. Let's say we're given a joint distribution. Do I have a? Okay, I'll show you with this hand. We're on pairs AB, where A is between 1 and n, B is between 1 and m. And without loss of generality, let's assume that n is greater than or equal to m. Okay, so it could be that they're the same. So we've got this joint distribution, and of course we want to test if it's independent. Is it equal to the product of its marginals? Okay, well, one idea is to use the closeness test. Okay, so I'd want to say, well, if I have this distribution P, I want to test, is it close to the product of its marginals? I can actually make my own, using P, I can make my own black box for P1 cross P2, the product of the marginals. What would I do? I take a sample from P and ignore the second coordinate. Okay, so that gives me a sample of P1. And then I take another sample, it's independent, and ignore the first coordinate. That gives me a sample of P2. So using those 2 samples and putting them together, I get a sample of P1 cross P2. Okay, so that's a product of the marginals. So I can make this black box from this black box, and now I can use the regular closeness testing ideas to see if they're close or far. Okay, and we have limits that say that if you're close to independent, then you must be close to the product of your marginals. So we know that. Okay, well, so based on that, you get something. It's not the best. It turns out there's another thing you can do is just learn these marginals, like actually sample them to death and learn these marginals. And that's another way to figure out the product of the marginals. That gives you a different complexity. And they're both good in different regimes. So if you paste them together, it turns out you can use a filtering scheme to paste them together. You get order n to the 2/3, m to the 2/3. But I don't want to say too much about that because it's been improved. So that was the first way of doing things. Again, there we had a lower bound that was wrong for the same reasons as the closeness testing. That was not improved by the Valiant 2008 result because his result only worked for symmetric properties. But more recently, I think in 2011 or 2010, we actually showed that those ideas do work for the independence testing problems, and n to the 2/3, m to the 1/3 is the right answer. So you might say that is a weird thing. It's not even symmetric in n and m. Remember, without loss of generality, we assumed n is bigger than m. So note that if n is equal to m, then this just gives you square root the domain size, right? Because both of them are n is equal to m, so you're getting omega n. But the domain size was n squared. Okay, so that's just to point that out. But then you have these weird dependencies that come from the closeness testing issue. Okay, so there again, so the lower bound is tight. There has been more work on the upper bound, getting it tight and getting it simpler and in a much nicer framework this is again all in the last year. Okay, so let me move now to some other types of properties. Let's talk about information theoretic properties, such as entropy, support size, compressibility. When I was working at NEC, when we first started working on these problems, I was at NEC Research Institute, which was basically a vision of NEC that there should be computer scientists and there should be physicists. But every person in each field had to have somebody on their evaluation committee from the other field. And we in computer science were lucky enough to have somebody who I think is quite familiar to this community, Bill Bialik. I think to many of you he should be familiar. And he was on my evaluation committee, and thanks to him, I found out we were working on the same problem. So it was really good that he was evaluating me, and that was the beginning of a long friendship. So let's talk about estimating entropy. And let me start with the issue of multiplicative approximations for entropy. So of course, like if I want to multiplicatively approximate my entropy of a source, in general, no, you can't do it. Why? Because if it's really, really, really close to zero, you're never going to see anything but that main element, right? So, and how do you know if you just haven't sampled enough, or, it's really hard to approximate zero, basically. So let's skip that weird case, and let's say that you're told the entropy is bigger. It's at least a constant, okay? Well, then you can gamma multiplicatively approximate the entropy to within, to factor gamma, multiplicatively approximate the entropy, and you only need n to the 1 over gamma squared samples. So let's just take an example. Let's say you are willing to handle a 4 multiplicative approximation. Just within a factor of 4, you only need n to the 1 over 16th many samples. Okay? And so this is quite sublinear. And Valiant showed that this was tight, again, based on his symmetric properties. And in fact, you can do better when you know that the support size is small. And I should mention also that a similar thing happens for estimating the support size. Okay, and this is work by these guys. All right, so, but now we have a similar property. What if we have a similar behavior to what we saw in the closeness testing. If you're willing to handle a multiplicative approximation, you can get way sublinearly many samples. If you want an additive approximation to the entropy, or an additive approximation to the support size, then you do need n over log n samples, theta n over log n samples. Okay, it's still sublinear, but not quite as dramatic as what we had before. Okay, and this is where Wu Yang have simplified the works of Valiant. So these guys, Raskolnikova et al. Got n to the 1 minus little o of 1, lower bound, and Valiant showed a better lower bound, and then Valiant showed kind of the tight n over log n bounds. Okay, and then Wu Yang simplified and I think got better dependence on epsilon. And this is both for entropy and support size. These are the things. So I also want to mention compressibility of data. Well, when we talk about, here we're talking about estimating the compression, not actually computing the compression, okay? I'm just trying to estimate how much can I compress this without actually doing the computation. So, as we know, the question then is, according to which compression regime? Well, just to ask if a set of strings is, like how well compressible is a string, we know that problem is undecidable, but you can estimate run length encoding in sublinear time. You can get a multiplicative additive estimate there. Huffman coding is essentially like estimating entropy. We saw that you can do that. And we saw how you can do that multiplicatively, you can do that additively. And Lempel-Ziv 77, I think it's 77, turns out to be, we can show a relationship between Lempel-Ziv and the support size. Okay, so it's, you need to prove something there, but you can show that it's exactly like estimating support size, and then you can use the bounds that we just showed you for support size. And you can estimate this in n over log n. Okay, so let me just mention another model, which is up till now we've been assuming you have one distribution, maybe two. What about properties of collections of distributions? Maybe you have a ton of distributions on sales in different states and you want to compare them all. You might want to ask, are all the distributions equal? Okay, so that's actually another way of expressing the independence testing problem. You might ask, can they all be clustered into k groups of similar distributions? You might ask, do they all have the same mean? That's very similar to an ANOVA type problem, but it's a bit different because there are no assumptions made on the form of the distributions as there are in ANOVA. ANOVA assumes that everything has the same variance and that they have and that they're normally distributed. Okay, so here we don't make those assumptions. On the other hand, it's more of a it's weaker in the sense that it's a property testing version of ANOVA. ANOVA is analysis of variance. And there's been quite a bit of work on this as well. In fact, some might or might not be mentioned this afternoon. Okay, so there's a lot of other questions you can ask. So this is a model that hasn't been studied very much, this notion of testing collections. There's lots of open questions here. I'm just going to put some of them here. You could ask if the means are in monotone increasing, k flat. You could ask all kinds of questions that haven't been asked. I mean, I think it's sort of an open area, which we've just started looking at. But I want to say that it's actually relevant in certain visualization and database type questions. And in fact, Mariam and I have been working with people in databases in visualization to try to see if we can solve some of their problems in this model. Okay, so I want to say a bit about testing via shape. So we've talked about testing closeness. We've talked about information theoretic questions. So far, everything has been sort of symmetric properties of distribution. Now I want to move a little bit to distributions where they're not so symmetric. There's a notion of the shape of the distribution. So, okay, so now, you still have, your domain is, let's think of it as a total order. It could be a partial order, but for now, think of it as a total order. And you've got some sort of shape going on. It's like monotone increasing, monotone decreasing. Maybe it's k-modal. It goes up and down k times. Maybe, it's a Poisson distribution, a binomial distribution, a PBD. This is, you'll hear more about that this afternoon, I think. Yes? Okay, good. A log concave. There's all sorts of shapes out there, okay? And we'd like to somehow use the shape to help our testing algorithms. Okay, so let me mention another important shape that's used quite a bit actually in database representations of distributions. And that is k-flat distributions or k-histogram distributions. Those are two names for the same thing, okay? What are these? You have this domain 1 through n. You can partition it into k contiguous pieces. And then the probability distribution function is flat on each of the pieces. Okay, that's a k-histogram or a k-flat distribution. Okay, so we're constant. So you can also k-piecewise constant. That's another name. Okay, everybody uses all of these names. And why are we interested in k-histograms? They're pretty good at approximating things. They're pretty good at approximating real data. And what we're going to see is they're actually really good at approximating these kinds of families. Okay, so that's what we're going to try to do. We're going to try to come up with a general framework that looks at things in terms of k-histograms, and then figures out what k should be, and uses this k-histogram approximation in order to solve the testing problem. Okay, so the strategy is going to be find a k-flat partition of the domain, estimate the weights of the k-flats, and then try to figure out if this concise approximation of our distribution is close to the property. Okay, and it's not going to be so simple because we have to figure out what should k be, and we should also figure out how do we find a k-flat partition of the domain. We can't assume that the algorithm has any properties. So we have to know, we have to know in this little area, is the distribution going like that, or is it looking like that? So we have to figure out how to determine these things, okay? So that's going to be the issues that we're going to deal with here. This is going to be, once we find that partition, this is going to be simple, and this is going to be something we're going to have to prove theorems about, but it's not going to require new samples, okay? So this is going to be the main difficulty in terms of samples. This is going to pretty much follow from these samples, But and then this is not going to require any new samples, but will require some theorems. Okay. All right, let's just, as an example, give monotone distributions. Okay, so monotone distributions over totally ordered domains, let's say I less than j implies that p sub I is less than p sub j. So these are monotone increasing. Later in the talk, I'll have monotone decreasing. I hope you can make that shift when you need to. We'll see if you're awake. Okay, so now testing if a distribution is monotone is going to require root n samples. Why? Well, there's like a simple reduction from uniformity testing. We know that your distribution is uniform if and only if it's both close to monotone increasing and close to monotone decreasing. Okay? So if you could do monotonicity testing faster than root n, you'd also be able to do uniformity testing faster than root n, in which case, we know you can't. So we do need root n samples, but the question is, how do we even get root n samples from monotonicity tester? And I'm not going to explain to you the original way of doing it. I'm going to explain to you a better way due to Daskalakis, Diakonikoulos, and Servetio. What you're going to do is use this thing that they call the Birge decomposition, Birge decomposition. You're going to partition the domain into exponentially increasing sized buckets. Okay? Each bucket, the ith bucket is going to be size 1 plus epsilon to the I. Okay, so these are getting bigger exponentially. You only need logarithmically many buckets. Okay? So these are contiguous. You've got this domain, here's your first bucket, here's your next bucket, here's your next bucket, and this is going to just keep getting bigger exponentially, okay? All right, now let p hat be the distribution that's uniform on each bucket, okay, but so we want p hat to be like p in terms of the weight it assigns to the bucket. It'll give the same weight to each bucket that p gives to the bucket, but it'll be uniform on the bucket, okay? And that's the Birge approximation. Okay, well, what's cool about this, and it's really cool, is that these bucket and endpoints were determined in advance without even looking at the distribution, okay? It turns out that, I didn't say that. Did I say that? Okay, here's the thing that is missing from this. Oh yeah, I did. There it is. Okay, so p hat is what you get when you approximate p. But how good is this approximation? This is the theorem that these guys show. What is it? That this approximation is really good. It's within epsilon if you pick the right number of buckets. Okay, if you spread this into enough buckets, and the number of buckets isn't that big. It's like 1 over epsilon log n. Not so big. You know the endpoints and start points in advance, obliviously. It's great. This is fantastic, basically, I think. Okay, so you have this thing. You know in advance how to split everything up. You just have to estimate these weights. Okay, that's just log n different weights. You just sample it, you're done. That's the whole thing. And then these guys had this theorem that tells you whatever you did, if you started with a monotone distribution, you're going to end up epsilon close. So you didn't change by much. Great, so that's a reason to be excited about this, but notice that I said, assuming you started with a monotone distribution, then this thing is a good approximation. But we don't know that the thing was monotone. We have to test that. All right, but this is just a reason why k-histograms, log n histograms, are really good at approximating monotone distributions. Okay, so what we want to do now is approximate our distribution by k-flat distributions. We want to partition the domain into k intervals. For monotone, k is going to be logarithmic. Actually, for most of our other examples, k is going to be logarithmic too. But, that's good. And then we're going to hope that the conditional distribution is uniform in each. And then when we finally get this thing done, we're going to check if our k-flat distribution is close to being in the class. Okay, so we can check if it's close to being in monotone. That will fall out pretty straightforwardly. But okay, so what's the question? First, you want to know, can you approximate all the distributions in this class by a k-flat distribution for small k? So we just saw that for monotone distributions, you can do it for k equals logarithmic. Then you have to ask, how do you find the interval boundaries? Well, for monotone, it's given to you in advance. These guys gave it to you in advance, okay? For others, you might actually have to look for the interval boundaries. But for this k, you know in advance. And then you have to check if the k-flat distribution is close to the class, and there's a little bit of an issue because you have to solve a linear program, okay? So what I want to point out is that the uniform distribution because of sampling error, if you took the uniform distribution and you did that Piaget bucketing on the uniform distribution, you can't expect, okay, just think what you would happen here. You estimate all these weights for the uniform distribution, okay? Now, it's not going to come out monotone because you have sampling error, right? So, so you have to factor in what happens. You got sampling. You can't check, did my numbers come out monotone? You have to say, are they close in some sense? Okay, how do you do that? Well, it turns out that in general, this is something where you just need to solve a linear program. You need to figure out how to state the linear program. For monotone, it's easier than for the other properties, but you need to solve some kind of linear programming on log n variables. So don't get scared. Okay, it's pretty. You could almost do brute force, but you don't want to. Okay, so let me. I think I'm going to sort of run out of time. So I just want to say that in general, the idea. I could do it. Okay, maybe I'll do it. Okay, the idea for finding a k-flat distribution is you can recursively partition your ranges in half, unless either you got to a point where the probability weight of that partition is so small that it's not going to affect much, or that you did a uniformity test there and you saw it's pretty close to uniform, so you might as well just use like a single flat for that and not keep subdividing it. Okay, so once you see that you've gotten to a partition that's close to uniform, then you don't need to subdivide that anymore. And that's the idea. Okay, so this is where your root n samples is going to happen, because you're going to do these uniformity tests in your partitioning. Okay? And then if you find that you partitioned the thing too much and you still didn't get to stop, then you know this thing can't be in the class. Let's just do an example to make that clear. All right, so here's some distribution. I'd like to see if it's monotone. What am I going to do? Well, first I have my whole domain. That's 1 through n. I subpartition it into 2 halves, right? And now, okay, both of them have enough probability that I'm not going to, remember, here's the algorithm. If the weight of the partition was small, then I just stop, right? Well, here, both of them have enough weight that I'm not going to stop. So what I need to do is uniformity tests. But notice that everything is uniform given that I'm in the first half of the domain, and uniform given that I'm in the second half of the domain. So these guys will pass their uniformity tests, and I'll just stop there. That's the whole partition. Okay, so I'll partition it into 2. I chose this easy case so you could see the algorithm. Okay, all right, so you can, so you do this too. This thing passes the uniformity test, you're done. Okay, let's do something slightly more complicated. Let's do an exponentially increasing probability distribution. What happens here? Well, you divide this thing in half. Okay, the first half has like negligible probability, so you don't go down there. You don't go down that branch at all anymore. Okay, and this half has enough probability that you'll do a uniformity test and you will fail, because it's not anywhere near uniform. So you recursively break this up. Okay, now when you recursively break this up, this 5 and 6 are still going to be, well, if this was bigger, if this was a big example, the n over 2 plus 1 to 3 n over 4 is still going to be negligible. Okay, so this is you're never going to go down this path anymore. You're just going to stop. But you're going to do a uniformity test here, and you're still going to fail. And this is going to just keep happening for a long time until you get to a complete binary tree down here, which is going to be, it's going to tell you exactly the last log n buckets. Okay, so that's what's going to happen there. All right, so this type of approach can be applied to all these families: monotone, k-modal, log concave, monotone hazard rate, binomial, Poisson binomial, k-histograms, k-piecewise, degree D polynomials, k-sums of independent integer random values, all these things. And that's the type of approach that could be applied to these. So this is just some history. It didn't all happen at once, but eventually it became a general testing paradigm. And there's even more improvements due to Clement, so you can ask him about it later. I want to mention that this is not the only way that these properties were tested. So for example, there's another general paradigm that handles most of the same sets of classes by Acharya et al. And all of these classes were also attacked sort of one by one by other works as well. So I just want to mention that. I want to mention also that, I've mentioned a whole range of properties to look at of distributions. There's still more. And I'm just going to give a few examples here, such as limited independence. Is your distribution k-wise independent? Are you monotone over a general post set instead of a total order? This afternoon, there's a talk about junta distributions. Those are distributions that depend on few of the coordinates and you're trying to figure out whether it's a junta distribution or not, and lots more. Okay. So I want to also stress that there's a lot of open questions here, things that there's a lot of excitement going on in the field. There are a lot of papers, but there's still a lot more to do. We've just gotten started. So here's just some ideas to throw out of problems that people really haven't looked at that much. Higher dimensional flat distributions, mixtures of K-Gaussians, generated by a small Markovian process. Anything where you can sort of beat the learning bounds, I think, is interesting. Okay, so I want to just a word about the dependence on n. All these algorithms that I've told you about are little o of n, but they're usually n to the alpha for some alpha that's, between 0 and 1. Okay, so it's like n to the 4th or something like that. Well, like if you're using this for you're trying to test your pseudorandom generator and see if it's good for cryptographic purposes, then no good, right? Because that's like you're thinking of the domain size is actually 2 to the n, right? And you just would never get started. So this is a non-trivial type result, but it's still kind of daunting in certain applications, let's say. All right, so what do people do to get past the lower bounds? Well, you can always restrict the class of distributions. You can say, okay, I can test k-modal distributions for monotonicity, or like I'm given something about my distribution, but not the full thing that I care about. Like I'm told some property about it, but I want to know if it has a stronger property. Okay, so that's so you can test certain structured distributions. Most of these early works were just on up to here. We're assuming that the distribution was known to be monotone. What further thing can you test about it? But this more recent work makes much weaker assumptions on what's known about the structure distribution. That's the Nicholas et al. Paper. Another thing that people look at is something called competitive closeness testing. Essentially, what you want there is an idea of like, okay, some distributions are easy to distinguish. So for those, I'd like to do better than the worst case bound. Okay, so this is something that's been studied quite a bit, and there's some really interesting results here as well. And people have looked at other distance measures. I'm sure somebody's going to ask me, what about KL divergence? So let me head that one off. So somebody always asks me about KL divergence. So just the difficulty with KL divergence is you can sort of show an infinite lower bound. And that's just because if one, you know about KL divergence better than I do, but if like one distribution has slightly positive probability and the other one has 0 probability, how are you going to find that? And then your KL divergence is infinite, so you can't hope to do that. But there are other information theoretic measures that are kind of close to KL divergence that people have looked at. Okay. Also, what happens when you get more powerful query models? I'm not going to talk about that at all today, but I should mention that Clément wrote a really nice survey about this. So basically, you can assume that I'll just make a plug for it. So remember when Google put out their n-gram information? Okay, so that actually gives you not just samples. You can not only sample their set of, so they had the n-gram information. They also gave the data that they computed it off of it. So you could sort of take a random sample from the n-gram information and get, a random sample of 2 words in a row, okay, or n words in a row. But you can also, because they computed for you, they did all this pre-processing, you can actually get probability distribution function queries. And you can simulate other kinds of queries from what they give you quite quickly as well. So you could, in some settings, assume a more powerful query model. Okay? And there are also situations in database settings where they actually do a lot of pre-computation for you. It's kind of generic. It's not specific to the problems you're trying to solve, but it does help you a lot. Okay, so these are other questions that may actually be interesting in practice. They can often give you logarithmic speed up. The speed up is exponential, not log. So I want to say that you can go from n to something like polylogarithmic in n by taking advantage of the fact that you're in a situation where you can make more powerful queries. Okay, so that's another thing people do. Okay, I'm done. Okay, so I'll spend a couple of minutes on this then. So so the title of the talk was testing and correcting. So I just want to say a couple of words about correcting, or maybe more than a couple. And so I want to talk about correcting probability distributions. And I think there's a lot of work done in this community on this problem already. So I just want to, I think this part of the talk is more questions than answers, okay? So just keep that in mind. But it's questions that I think come straight out of the cult community, like questions to frame these questions in terms of like cult type questions, okay? So so you're given, here's your samples of a distribution. They give you something that looks like that, and you want to correct it. What's correct? Does that look correct? Does that look correct? Which one do you prefer? I think I personally prefer this one, but maybe this would be the more usual type of thing that you'd want to go for. Okay, so what do you do with that kind of data? How do you fix sample data? Okay, I mean, I don't think I'm inventing a new question here for you guys. I think you've all seen this. And there's lots of buzzwords you can use, like outlier detection, removal imputation, missingness, and people have said all these things and they do certain things. So, great. But what if a lot of this work that is based on, say, assuming the distribution was supposed to be normal or was supposed to be Gaussian, or, that the noise was random, the noise was like this, and you're going to try to learn it and fix things, okay? So basically, the question is, can you do something better than learning? Okay, that's the real question for this part of the talk, okay? So, and in particular, let's first try to use sort of a cult-style definition here for what is it that we want to do. Let's assume that let's kind of propose a methodology that's a lot like the PAC learning model in this sense. Let's assume that the original distribution came from something close to a class P. Okay? Now, P does not have to be just Gaussians. Okay? P could be something much weaker, like it could be monotone or K-modal or K-histogram distributions. Or it could be anything. It could be something much more general, not necessarily, it has to be Gaussian with variance 1. Okay? And then I just don't know the mean. Right? But something much more general. And now what we'd like to do is we're given samples from this distribution that's assumed to be epsilon close to this class. We'd like to correct it by outputting samples according to Q prime, which is in the class, but still close to Q. Like we don't want Q prime to be over here. Okay? So that's the goal. Okay? And the goal is to come up with sample correctors that are good for a certain class of distributions as we do in PAC learning. Okay? So that's the idea. Okay, and now what's the question? What is the sample complexity per output sample of Q prime? Well, observation, but I mean, you can prove this. It's an observation which you can fairly easily prove, but if you have an agnostic learner for a distribution, then you can get a sample corrector, okay? And I'm not even going to define these things because I think you guys essentially get what I'm trying to say, and if you want definitions of agnostic and non-agnostic learners of distributions, come this afternoon and see at the talks. Okay, so, but what this does already, this observation already gives you sample correctors for all kinds of distributions, monotone distributions, histogram distributions under various promises, like that the distribution is MHR or monotone, and these already give you better observations than what we knew before, probably because we never thought to ask those questions, but it does already give you like immediate corollaries where you don't even have to work. Okay, so the big open question is, when can sample correctors be more efficient than agnostic learners? Okay, that's our big question. And for histogram distributions, it turns out you can do, okay, so I'm really borrowing words here from the cult community. This is a non-proper correcting. Okay, what would that be? Instead of here, where we wanted to correct the Q prime should be in P, we're letting Q prime to be in a slightly bigger class than P. Okay? So Q prime doesn't have to actually be in P, it just has to be in a bigger class than P. So we can actually do really fast non-proper correcting of histogram distributions. What do I mean by that? If I allow you a factor of 1 over epsilon more pieces in your histogram distributions, it's really easy for me to correct a K histogram. I can correct K histogram distributions by K over epsilon histogram distributions really easily, okay, and like constantly many samples. Okay, so that's a fairly, I need something about my histogram distribution that the max probability is bounded, but other than that, the work I need to do is really simple. Okay, for monotone distributions, we can correct faster than learning when the error is either really small, like by 1 over log squared n in L1 distance, or if I have access to more powerful queries, or if I know something about the errors, like that it's, like I'm missing data in a consecutive location. And that, of course, is a little bit, there you can learn where you're missing the data and try to correct for it in a certain way. Unfortunately, for monotone distributions, it doesn't seem that we can, in general, beat the learning algorithms, but I think that there's still some leeway here for what's left to be understood about monotone distributions. And again, this is just a beginning. There are tons of classes to look at in this model. So I would say this has a lot of open questions. Basically, for any class, this is interesting. I want to also mention for this crowd that we do know a little bit more. For example, if you have a sample corrector and a regular learner, that gives you an agnostic learner. So this might be good news for sample correctors. It might be bad news because it might lead you to lower bounds. It also, so there's another similar sort of way of strengthening testers to tolerant testers, which I'm not going to mention right now anyway. But let me just mention some, okay, so we're interested in when is correction easier than agnostic learning, when is correction easier than non-agnostic learning, and that's a bunch of open questions there. Let me conclude by saying that these distribution testing problems are everywhere. For many problems, we need a lot fewer samples than we might think. There's a lot of cool ideas and techniques out there. There's a lot of great colleagues to work with, and every day they come up with new things. So it's a lot of fun for me to work with these people, and that's all I have to say.